So I want to talk about one particular case that I'm familiar with because I do some work in computational genomics. So my read of the last roughly 10 years of the field is that early on there were these candidate gene studies in which people had very strong priors, very strong biological intuition that drove them to accept fairly low, fairly modest thresholds in terms of significance before they would assert that some gene actually had some causal effect. But then it took a long time for the community to understand that they should really be correcting for multiple testing. And now there's a standard of p-value of threshold of something like 5 × 10⁻⁸, which is corrected for the presence of, say, 1 million SNPs in the genome. And now things, as far as I understand, replicate routinely. And so it seems like an actual case of a community that learned over a period of 5 or 10 years of bad practices and eventually good practices. Maybe you could comment on what your perspective is on that.
I think that this is clearly a success story. And as you say, the replication rate of the candidate gene era, based on what we know now, was somewhere in the range of 1%, or maybe a little higher than that,
right.
But not
pretty
much
bad.
higher.
Yeah.
So about 95 to 99+% of what we thought we had discovered was not correct at that time. Conversely, pretty much everything that crosses a genome-wide significance threshold currently, I would say, has very, very high chances, or almost the opposite, 99% chance of being replicable. Clearly, this is a nice story, and the question is how much of that transformation could be applied to other fields. So more stringent statistical thresholds could be applied. One, there nevertheless runs the risk in some cases in fields where it's very difficult to come up with very large sample sizes that unavoidably the false negative rate will be very, very high in doing that. Then collaborative work and team science, which is another transformative principle that helped genomic epidemiology to mature, could be implemented almost in any field that I can think of. So the current example in most biomedical fields has been the siloed investigator kind of struggling with a small sample size to achieve something, which almost always is a false positive or close. And conversely, many other fields, physics, for example, has a very strong tradition in collaborative work and teamwork. And you can imagine how difficult it would have been, for example, to discover the Higgs boson if instead of having 10,000 scientists join forces and have one big experiment, say that we'll give an R1 to each one of 10,000 people, and each one of them has to deliver a Higgs boson within 4 years. We would get probably 10,000 Higgs bosons, but
all at the wrong mass.
So, and then the other major improvement was the accuracy of the measurements. So the field matured in terms of both the ability to measure in very large scale, but also the accuracy of the measurements. The error rate went down tremendously. Data sharing was also another contributor to this. People are willing to share data in that field far more than in other fields in biomedicine. How much of that is happening in other biomedical fields? Probably not that much. But of course, there's exceptions, and I think that we see more and more of these principles being adopted. But I suspect that if more fields could adapt their practices to adopt these principles, things would be much better. It wouldn't solve all the problems. So genetics has some advantages. For example, I don't have to worry that much about confounding. Conversely, if I'm trying to find out about what diet is best or different types of exposures, they're so heavily confounded with each other that it's very, very difficult in the absence of experimental studies to be able to understand what is real and what is just a confounded effect.